Hi everybody and welcome to the webinar CO2 Transport and Injection with LedaFlow. My name is Ludivine Rosevall and I'm the LedaFlow product owner at Kongsberg Digital. I will start today's webinar with a brief explanation of why CO2 modeling is critical to the carbon capture and storage technology. I will then introduce you to the joint industry projects which have been initiated to improve the current capabilities of LedaFlow to model CO2 transport and injection. I will then dive into the current LedaFlow models and advantages before I give you a quick demo, and I will make sure to keep some time at the end to answer your questions. So if you have any questions while I'm presenting, please post them in the chat and we will go through them together at the end. I'm not going to turn off the webcam. This is to ensure that you have the presentation on full screen, but I will turn it on again after the demo. Before I jump into the CO2 topic, I would like to just say a few words about LedaFlow in case some of you don't know much about it. So LedaFlow is a suite of products that have been developed to model multi-phase flow. Today we are going to speak mainly about LedaFlow engineering, which is a desktop application to model transient multi-phase flow. But we also have the LedaFlow point model, which is a steady state application. The LedaFlow integrated, which is a plugin to the dynamic process simulator in Kongsberg, and Cognitwin simulation, which is a cloud solution. LedaFlow is applied in various domains, and we are going to speak today specifically on about the flow assurance engineering applied to CO2. LedaFlow has been commercialized since 2011, and it is owned by a company called LedaFlow Technologies, which is itself owned by Total, Syntef, ConocoPhillips, and Kongsberg. So let's discuss a bit together the challenges of CO2 modeling. I guess since you are here today, you know that carbon capture and storage is a key technology to fulfill the net zero greenhouse gas emission targets that we have fixed for 2050. The idea is that the captured CO2 can be transported by long distance pipelines and injected into a reservoir for permanent storage. In order to do that, the energy industry needs good simulation tools. And you may think that, well, these simulation tools, they exist for the oil and gas industry, so it should be fairly easy to use them to model CO2 transport and injection. The thing is that CO2 behaves quite differently than other types of gas that we are used to in the energy industry. And the flow modeling of CO2 rich systems is currently an immature scientific discipline, at least when we compare it to the science of petroleum application. So let's have a look at these specific challenges that CO2 offer. So usually CO2 transport is restricted to single phase flow, mainly the supercritical or the liquid phase. This is due to the lack of confidence that we have for designing multi-phase flow systems. But in reality, two-phase flow is difficult to avoid. As soon as you have impurities, as you can see on that example, 2% of N2, the liquid can drop out and a two-phase region with a narrow phase envelope will be created. So these impurities will prevent you to stay in the single phase, or at least, yeah, will make it difficult to stay in the single phase. Also, it's difficult to avoid two-phase flow in the wellbore when, for example, injecting into low-pressure reservoirs. and also during shut-in and restart. What does it mean to have a narrow or no phase envelope at all? That means that small or no temperature change will occur during phase transition, and that can cause numerical issues. There is a very strong coupling between pressure and temperature, and we will see it in the demo case. The PVT properties are nonlinear near the critical point. And these two points here create challenges to normal operations and to the integrity of transport and injection systems. Last but not least, CO2 transport is about downward flow. And traditionally, we have only focused on upward flow because we were going from the reservoir to the processing facilities. Here we are going the other way around, and that is an unknown domain. I'm now going to briefly explain what are the R&D activities we are involved in order to address the challenges that I've just mentioned. On this slide, you have a timeline of the joint industry projects which have been initiated to improve the capabilities of LedaFlow to model the CO2 transport and injection. So I will go into the details of these three projects in the next slides. CO2 FACT project has been completed in 2022. The idea was to transfer the extensive experience that we had in flow assurance from the oil and gas industry to the CO2 transport and injection system. So during this project, experiments were performed at the IFE's Falcon Loop, both for pure CO2 and CO2 with impurities. We compared experimental data, field data with simulation results, and we established the best practices for using flow assurance software in CO2 pipeline transport and injection systems. So this project was managed by Equinor, as you can see on the right-hand side. At the end of this project, LedaFlow was validated for single-phase CO2. But when it came to CO2 with impurities, it was identified that more software development was required, and that is why we have initiated the CO2 Flow project. The CO2 Flow project is currently ongoing. It is managed by LedaFlow Technologies. And here the idea is really to focus on LedaFlow and make it a robust and accurate tool for CO2 simulations. That means improving the closure laws, improving the rapid phase transition prediction, improving the steady-state simulator such that it is possible to deal with complex CO2 injection networks. I'm going to show in the demo just a single wellbore, but we may have in reality many different wellbores, or at least different injection points. We also need to improve the numerical stability for transient CO2 rich flow. And in the end, we would also like to enable the prediction of CO2 dry ice particles. So I don't have any results to show from this project here, but some have been presented during the TCCS conference this year. And the industry partners that you see on the right-hand side, they receive regularly R&D releases, which are very promising. So we hope to be able to release it to the market quite soon. Finally, this JEDECO2 project is a little bit different. Here, the project manager are Kongsberg and CMG. And the idea was to get a better understanding of the transient effect that is related to CO2 injection. Current flow assurance tools like LedaFlow, they tend to use fixed IPR curves. which is maybe not good enough. So, in order to increase this understanding of the transient effect, we need to have a detailed near wellbore reservoir model that will provide a complex IPR to these flow assurance tools. So here the objective is to develop a controller that can integrate and manage the interaction between LedaFlow and a reservoir model that in this case is GEM. Okay, so let's dive now into the current capabilities of LedaFlow, what LedaFlow already offers for CO2 modeling. Obviously, modeling accurately the fluid flowing in pipeline and wells is very important, and LedaFlow offers several options for this. Among them, you have composition tracking, which is used to track each component of a fluid composition that is defined at the inlet, and to resolve the composition of each phase along the pipeline. It uses a direct link to Multiflash, a PVT package that is commercialized by KBC and that is available in LedaFlow. So through Multiflash, LedaFlow supports many equations of states, and to simulate pure CO2, it is recommended to use the Span and Wagner equation. For CO2 with impurities, it is a bit more uncertain what to recommend, but RKSA is a good starting point, at least until the CO2 flow GIP is completed. When doing dynamic simulations, pipelines and wells are divided into control volumes that we call cells. For each cell, LedaFlow solves a total of 16 equations. It solves the mass balance equation for all 9 fields, so the 3 continuous phases, gas, oil, and water, and the 6 dispersed phases, while momentum and energy equations are solved for the 3 zones. That means the continuous phases with the dispersed fields in it. Even though there are 3 momentum equations, there are 9 potential velocities through the drift flux model. And the volume equation completes this equation set so that both mass and volumes are conserved at all times, which is very important for fast transients like fluid hammer. The equation sets on the previous slides are solved according to a solution algorithm that starts with the update of the physical properties. Then it solves the momentum and the mass equation in an iteration loop before solving the energy equation. This is very computationally efficient for oil and gas systems. So that's what you see under the standard solution on that slide. But for systems with pure components, where the density depends very strongly on the temperature, this may cause unphysical oscillations, especially when the time step is small. So the solver strategy has been modified such that the energy equation is included in the iteration loop until energy, momentum, and mass are conserved at the same time. Note that the PVT properties are also updated during the iterations, which provides a fully implicit solution for the density and the enthalpy. As LedaFlow solves separate energy equations for all 3 phases, we have much more accurate information during stratified flow and depressurization operations, because in these configurations, the gas and liquid temperatures are expected to be at different temperatures. So the energy equation in LedaFlow that you see at the top is solved for the enthalpy, not for the temperature, which is a huge advantage when modeling CO2. In addition to those 3 energy equations, the dynamic wall model accounts for heat transient conduction in the pipe wall. So the pipe walls are made of concentric layers of material described by their respective thicknesses, heat capacities, densities, and conductivities. And it is also possible to model the formation around the wellbore with multiple layers. Since this is a transient model, it accounts for the storage and dissipation of heat. But the actual conduction is neglected as the ratio between the length of a cell and the pipe diameter is often very large. In addition to this wall model, we have a partially buried pipe model that provides the user with a heat conduction model from the inner surface of the pipe through the exterior surface of the soil. This is particularly important for estimating corrosion rates and pipe wall temperatures, information that is also critical for material selection. So the model, this partially buried pipe model, will preferably use for partially buried pipes, not for wellbore formation, for example. Finally, we have an annulus model that can be used to model the thermohydraulics of multiphase flow in an annulus on the outside of the pipe. It calculates the heat transfer from the exterior of the base pipe to the fluid in the annulus by convection, conduction, and radiation. It is also possible to specify the eccentricity of the annulus, which will have an impact on the pressure drop, but it doesn't. The eccentricity is not taken into account for the heat transfer. LedaFlow offers two hydrodynamic models, the standard model and the slug capturing model. The standard model is based on a unit cell model, which switches between flow regimes determined by physics-based transition criteria, so stratified, annular, slug, churn, and bubbly flow. What is important is that this unit cell model ensures a continuous flow regime transition, a consistent flow regime model for downward flow, and also the correct treatment of the bubble turning. The bubble turning prediction is very important for downward slug flow, as the bubble will either travel faster or slower than the bulk. So if this is not handled correctly, there will be jumps in pressure drop and hold up and numerical stabilities issues. So fortunately, LedaFlow handles that correctly. Last advantage, we have a single component systems, for single component system, a special non-equilibrium mass transfer that accounts for boiling and condensation. The rate of mass transfer scales linearly with the wall and interface surface area and the degree of subcooling. This means that the phase change is governed by the heat transfer rate and not by diffusion. This mass transfer allows us to model the phase change of CO2 without doing any flash calculation. So we don't perform any flash anywhere in the pipe except at the boundary nodes, obviously to determine what the phase split is. Okay, here I have a table that summarizes the main advantages of LedaFlow for CO2 modeling. That concludes this presentation. So I'm not going into the detail. I'm going directly to the demo. Since we don't have much time today, I've prepared a model in advance and run it. So what I'm going to do now is to present you the model and present you the results. As you can see, the model is a wellbore with a choke at the wellhead and a device at the bottom of the well to model the perforated zone where the CO2 is going to enter the reservoir. We are modeling the fluid using multi-flash. It is pure CO2, and we use the thermodynamic model CO2 pure, which corresponds to the Span and Wagner equation of state. Looking at the wellhead, we have a pressure of 90 bar and 4 degrees. That means that CO2 is entering the wellbore at 90 bar and 4 degrees. If I plot the results now, the choke is so close to the pressure node that we will not be able to see anything of what is happening at the wellhead. So in order to understand at which state CO2 is entering in the wellbore, we need or we can use the PVT tools and plot the volume fraction at 90 bar and between 0 and 10 degrees. At these conditions, we can see that we have liquid phase. So that means that the CO2 is entering the wellbore in the liquid phase. Now let's have a look at the most relevant profile variables. So here you have in blue the profile of the wellbore, and in red and green the volume fractions of gas and liquid. What we see is that after the choke we are in the two-phase region. So we have both gas and liquid until the bottom of the well, where we are again in the liquid phase. So that means that we are injected liquid CO2 in the reservoir. Let's have a look at the temperatures now. I'm going to activate the value tracker so we can have a look at the values in the legend. We see that we have a temperature of minus 24 degrees at the wellhead, which is quite low and very different as well from the 4 degrees we have entered at the wellhead or the pressure node. So we need to understand what is happening, especially because minus 24 is too cold for standard steel, which means that if that is verified, that will have an impact on the material selection. At the bottom of the well, we have a temperature of 16 degrees, which is quite acceptable. The bottom hole temperature is important for the integrity of the reservoir, but here there shouldn't be any problem. You may have noticed that we have a negative flow rate, and that's because, as you can see with the direction of the arrow here, the fluid is going in the reverse direction compared to this arrow. So that's why we have a negative flow here. So let's have a look at what is happening at the choke valve. If we look at the pressure drop, we see that we have a pressure drop of 90 bar. The upstream pressure is 90 bar. That's the wellhead pressure. And the downstream pressure is 20 bar. That explains the very low temperature. We have a constant enthalpy, so if we have a pressure change, that will result in a temperature change, and that is what we see here. And we know that CO2 cases are very sensitive to the changes of pressure and temperature. So that was what I wanted to show you today. It's just a simple case in order to show you how important it is to model CO2 in order to understand what can happen in a wellbore, for example.